Okay, so this section we will talk about the color and some of the application. First of all, this slide is tell us about the importance of the color. So that said, no matter how nutrition it is, how variable it is, if the color is not good, people will not buy it. So no matter the basis or habits or given area, certain food groups accept only if they fall within a certain of color array. So give you an example. For example, in the United States, we want meat. Okay, or red meat. Let's say a beef. We want it to be bright red color. That's what we want. And a chicken meat, we want it to be white and gray color. If you see a meat which is brownish color, that may be indicate it's old, it's oxidized. If you see a chicken meat which is grayish shoulder, maybe spoiled. So that tells you it is important to eat, to purchase or to consume based on the colors, because that's the first obvious vision you see from the products. Okay, so we will talk about a little bit detail of these colors, including measurements. First of all is some of the definition. This is directly coming from the textbook. Some of them we read over, one of them I want to explain. So first of all, what is a color? Visual perceived property of a material, which means a vision, how our eye feeling it. But you also should know our eye sensing the color compared to our feeling. There is a difference between the gap of our brain neural system and our eye sensing. And we'll mention it real quick. The second one is what is called current. That means a substance that produces color in a material. Therefore, we come out with another definition, which is called a dye and a pigment. Of course, those are chemical compounds with color or current chemical compounds. Okay, there is something I want to mention here is a lake. This is not really the lake what we talk about. This is the one we usually talk about is oil-rich foods. In the oil-rich foods, those currents cannot be usually not in a high amount in water soluble, in water solutions or water solvents. So therefore, we need to make sure the dye still can go there. Now usually it's about 20 to 25% of the dye in there. So we need some of the help. Therefore, we use calcium and aluminum salts. So therefore, we use salts. And then this will be expanded into the whole system, kind of like an emulsification system. Therefore, looks like a lake. That's why we give the name called a lake. Usually, for oil-rich foods, the water-soluble currents is not available to use, so we make those as salts. Then it can be expanded into the system, looks like a lake. This is one of the examples. Another example is in a canned food. In a canned food, you know that canned food, these are the metal. If it's reacted, the canned food has been there longer time, usually it will be reacted with protein, with currents. That's called tin. If the tin is there reacted with the ingredients, sometimes it will cause color change. For example, anthocyanin. We'll mention this real quick. If they reacted with the canned foods, with the metal there, they will become purple. This is also a phenomenon called a lake. So anyway, this means the currents has been reacted with salts or reacted with metal products in a food product. That is called a lake. Now we also want to talk about the certified. Now what means a certified? Every dye, or we say colorants used in the food products, you have to be approved by the FDA. They need to give you a number, which is usually we call FDST number. This means food. That indicates FD means drug, C means cosmetic. They have a number. For example, FDC red 40, that is the color, red color allowed to use in the food processing. Other than that, it's not really legally to be used. So that's called certified. Now we do have some exempt, which means colorants usually derived from nature, but be careful. Not all the colorants from the nature is allowed to use. Some of them derived from nature, or they are equivalent to a synthetic chemicals. They can be exempt from US certification. A good example is beta-carotenoids, or some of those juice, or let's say vegetable juice. If you want to use vegetable juice as a colorant, those sometimes do not require to be certified. So these are the definitions. Now let's look at here. Some more. Any colorant added to a food or beverage for the sole purpose of coloring must be labeled an artificial color. They must be labeled. For example, natural colored with what kind of juice, colored with juice, and what kind of color. Now, usually the synthetic colorants, they are all very cheaper, easy to be prepared, water soluble, very stable, longer shelf lifetime, can produce very brilliant colors to attract customers, and strictly regulated by FDA. Well, of course, country by country, they have some of the differences. Here is strictly regulated by FDA. Here gives you a table, which is the example of all these certified synthetic color to be allowed use in the food processing. Okay, so blue, let's say FDC blue number 1, we call it brilliant blue FCF, triphenol methane. How about that? Stable to heat, unstable to light. So you can see blue, you have number 1, number 2, green number 3, red number 3, number 4, yellow number 5, number 6, orange, the circus red number 2. All these are approved to be used, have a corresponding common name and a chemical name for that. And the here, which is listed, how they stable to the light and the heat, sometimes for the acid. Now, all the color change during the food processing most likely will be impacted by light, heat, and acid. And we will mention these one by one later on. Now, how about the natural color? That colors exempt from certification. The colors of foods are the result of natural pigments or added colorants. They are usually not certified, naturally presenting animal and vegetable products. And basically they have 4 groups. We will mention lots of them a little bit, pretty much detailed. First group is tetrapyral group, chlorophyll hemming and bindings. Second, isoparanoids derivatives, carotenoids, benzopyrene, isocyanin, and flavonoids. Last one, artifacts. This is not really natural, this is coming from the reaction, but the reaction we cannot avoid. Melanoidin coming from Maillard reaction, caramels coming from caramelization. Okay, so this is just give you some example of the natural pigments. But we mentioned about earlier, just because it's natural does not mean it's permitted for using. Now, very careful. In the local level, lots of people will mess up with the concept of natural and organic. Now, if your product is certified as organic, then the colorants, even its natural colorants, has to be certified with the Organic Association, which is in their approved list. So does not mean it's natural, you can just use it, or just say it's organic. It's a different story. Now, usually the natural colorants, they are expensive. They are less vivid and intense. They have increased microbial safety risk because they do not have any of the antimicrobials. Another one is they are less stable to heat, light, oxygen, and metal, so highly reactive. Okay, so just give you an overall idea about those natural colors. So talk about in here, we're going to talk about some of the evaluation system. How we measure the color of our food products. They basically have like 1, 2, 3, 4, have 4 systems. So we want to measure them. So first one is called a CIE system. Where this comes from? This is called a commission. CIE system, long time ago, is an international standard. That's called International Commission of Illumination. Then, why this is not called ICI? Why it's called CIE? C also represents commission. I is international. E, which is rage. This is a French word. I don't know how to pronounce it very well. So this is equals meaning of illumination. So this word coming from a combination between English and French. That's why we call it CIE. Basically, the meaning International Commission of Illumination. It's an association for standardization of color. Now, CIE system is a trichromatic system, which indicates how our eyes feeling about color, which is sensing of our eye. However, without the connection of the brain neural system. So just our eye, how we sense it. And basically, we differentiate them into 3 major colors, which is red, blue, and green. Red, green, and blue. Now the idea is, if we know the index, every 3 of them have a number. If we know 2 of the numbers, then we will know the other one. So this is kind of like you do a math. Just give you a brief example. If we say this is ABC, and we know they add together equals 1. If we know A and B, or B and C, we will know the other one, A, B, C. So let's say this is P. Okay, we want to know the distance between P to the right angle. Sorry, just write a little bit. So how are we going to do it? We'll of course draw like this. This is G. So let's say this is B. This is C, this is A. This is C. Now we know A added B added C equals 1. And this is also we know A added B added C equals 1. So therefore you know, if this is 45 degree, this is 45 degree, we know this location is B. This is kind of like B and C. So the point of P, kind of like B, C, and B. And if we really want to know the difference, the distance go here. Okay, we know this one calculated by square B plus add C add B. So just give an example. Any of the weeds they think about, all of the color fits in this triangle. Any of this could be expressed by ABC. Either 2 of them or 3 of them. And ABC added plus together equals 1. So we know 2 of the value, we know the third value. That's all of these values represents red, green, and blue. Okay, just briefly. So this is the CIE system. Now, how the machine really calculated it? First of all, the CI system, we are using the X bar, they're called Y bar and Z bar. This is so-called tri-stimulus system. Tri-stimulus system. Okay, we have these. And each of them actually indicate a wavelength, the peak value here. Each of them. X usually is red, Y is green, Z is blue. So you have this curve there. Now, how you come out from that one? This is indicate X is X bar divided by add Y add Z. Then Y is Y bar divided by X and Y and Z. Then we go get those. Okay, we have each standard color. We give X-axis, Y-axis, give the value. So you're gonna come out with this. And then each of them, you have these type of the line. This is called locus. LOCUS, that's what it comes. So this is just briefly tells you how they comes out, these standards. They first of all get the peak value, then each individual color spectrum, the color, they measure the value of the X bar divided by those three. And then they do the X and the Y axis, then coming out this color spectrum, and each rectangle, it represents a different color, and each line they call it a locus. Okay, so based on this is the machine has already set up. What means red? Is X equals 1, Y equals 0. What is green? X equals 0, Y equals 1. Then what is blue? X equals 0, Y equals 0. So this is here is just to briefly tell you how the system is working. Then we give an example. This is the USDS standard maple syrup. Using this system, use the measurements. It's a machine. It's like a computer's calculator programmed system. They find the maple syrup is right there. Okay? So then they go ahead to find the number. X equals 0.486. Y equals 0.447. T is 38.9%. So what that means? Which means this maple syrup, 48.6% is primary red, 47% is primary green, and 6.7% is blue. So how we get that 6.7? Of course, it's 1 minus X, 1 minus 0.486, and minus 0.447. Then we know blue. What is that T mean? That means how much is the light transmitted. So the light transmittance is 38.9%. So here you should know, any of these machine measurements is data tells you the three standards, three level, three index. Each index have a different level. Then you know how red it is, how green it is, and how blue it is. Not only is a single number, it's a combination of a three number. So this is the first system. The second system is a Mansell system. Okay, a little bit of difference. Here we are talking about is a cubic system. Three items here is hue. You look at this circle. The hue, which is we talk about red, yellow, green, blue, and purple. Then we talk about is that white or black. So we call it lightness. We give a score 0 to 10, which is this perpendicular line. That's called value. That's lightness. If 0 is black, 10 is very white. Then the diameter here, we call it chroma. The chroma usually indicates purity. And 0 for the central grid, which means purity. So give the example. If a color is 5R, 2.5, 3.7 in the Mounsell system, which means red hue 5 volt, value 2.8, chroma 3.7. Okay, so that's give you three numbers to mention this one. Mounsell system, I never heard about it, I never used it. It's just some of the people using this long time ago when the Hunter system, before the Hunter system comes out, they could measure the purple color of the meat because the purple color of the meat is related to the dullness, including rare, medium rare, well done. So this system can measure the hue. That's why they used a little bit in the meat industry. But now why do they use it? Okay, this low V-band system. Low V-band system is obviously measuring the color is yellow. Since it's mainly focused on is the yellow, which means obviously is used for measuring vegetable oil, because vegetable oil basically is yellow. So it's a very easy system. The light transmits through glass coverts filled with oil, and we have 4 different types of the filters: red, yellow, blue, and gray. So they give you example, which is a typical oil is R equals 1.7, which is 1.7 red, 17 which is yellow. That is usually a standard color for our oil. Anything changes. Let's say the red is increased, the yellow is decreased. What that means could be oxidation happens for the oil products. Okay, so just let you know, low V-band system most of the time is only for the vegetable oil. Now this is the one we basically really want to talk, and we will be practice this in the lab on Thursday, is for the Hunter system. So very simple, the Hunter system. Hunter system, which is an improvement for the CIE. This is the sensing of eye. And this is usually fill the gap of sensing of eye to the perceived with brain. So there is a gap between them. You know, if it's red, let's say we use a machine to measure, it's 100% red. We use our eye to feel about it, because there is a connection between the eye and the brain neural system. That might not be 100%. You only feel maybe 90%. There is a gap between that. So CI system cannot really to show the color coming from the consumers, but Hunter system will solve this problem. Now what are they measured? Really simple with 3 things. Is A star red color. B star is yellowness. L star is lightness. And this is widely used in the meat industry a lot, because we caring about this A red value. So you can see here the red is compared to green, is red to green dimension, A value. B value is yellow. If a red meat, let's say a chicken meat, even a chicken meat, which is red value should be negative. We'll mention that later on, should be negative. If the chicken meat, you see the A value is increased, and the B value is significantly increased, which means it's discolored. So I give you an example. A long time ago, people are using lactic acid to decontaminate the salmonella on the chicken wings. Then they use that a lot. They find it become yellow. There is a discoloration caused by lactic acid. Therefore, they want to solve the problem. They're using a buffering system called the lactic acid and the citric acid blender. That is what called chickside in our lab. That's a bottle which is coming from. Originally is to prevent the yellowness of the chicken legs. Because once the yellowness comes out, some oxidation happens. People may think about it, not really sometimes. So therefore, they're using a buffering system called chickside. Okay? So that's a B value. And the light L, which means lightness. So that's a counter system. All of the meters, the color meter using the lab is counter system. And that meter is expensive, somewhere between $20,000 to $50,000. So we're going to talk about these little bit one by one. Okay. I drew this picture last time. The first one is myoglobin. So what's a myoglobin looks like? If you still remember, this is we call, it is a Lewis base. So it's a tetropyral. Why we say it's a tetropyral? In the center is iron atoms, or ferric ions, connected by 4 ring, which is we call, it's called a pyral ring. Then the whole system, we call it a pulp ring. Now, most of the time, a meter color is actually determined by globin. The globin encoding 2, which is myoglobin and hemoglobin. This is a very large molecule, about 67 DA. This is a smaller one, about 19 DA. So this is actually times like more than times 3. Now hemoglobin, you know that, basically is attracting oxygen for the transport oxygen for the life. Myoglobin is more pay much attention for the color. So we originally thinking about both of them contribute for the meter color because they both are globin. But later on people find that myoglobin play more important role than hemoglobin. So they don't talk about this too much at all. In all the textbook, we folks talk about the myoglobin. Now, here we have the formula there. When we see it's a red, bright red color of the meat, is oxygen myoglobin. Once you see a purplish red, that's deoxymyoglobin. And sometimes during the cooking or during curing process, you see those brownish colors, that is metalmyoglobin. And we have another slide to talk about detail. So there is a connection between these, and those are all reversible. Okay? So we're going to talk a little bit about the meat color. So we mentioned in our tenderization section, meat color is of course impacted by post-mortem metabolism, including muscle pH. We want the pH to be holding 5.5. If the pH is too low, like 5.2, or below that, what happened? It's close to the isoelectric point. So the water